Hello and welcome to the very first lesson of our trigonometric functions unit. Today we are looking at Pythagorean theorem and our basic trigonometric ratios. And before we get started, we are going to do a bit of review of classification of triangles. So with triangles, you can either classify them based on their side lengths or based on their angles. So based on their side lengths, we can have an equilateral triangle which has all three sides that are equal in length. And when we have such a triangle, consequently, the angles are also the same and each angle will be 60 degrees. And when we draw this triangle, the side lengths are shown to be equal as so, and then the angles are shown to be equal this way as well. Now, we can also have an isosceles triangle, which has two sides that are equal length, and the angles that are adjacent to that triangle, or those side lengths, sorry, are going to be the same. So in this case, this side length is not equal to any other side length, but these two are the same. So we show that with the two dashes that those two side lengths are the same, and these two angles that are, sorry, it's hard to draw here. There we go. These two angles that are adjacent to those equal side lengths will also have an equal measurement. And this angle opposite to the base will have just its own angle that will be different. And finally, we have a scalene triangle, which has all sides that are different lengths, and all the internal angles will be different. Consider something like this, and we show that this has one side length, this has another, and all three sides are different. And same with the angles, we will show typically you match the ones that are opposite. So these are 2 and this one will be 3. So all of these 3 angles will be different. Now, with respect to the angle, when we classify triangles, we can have an acute triangle, which is that all the internal angles are less than 90 degrees. So pretty much both of these two are acute triangles. So equilateral will always be an acute triangle because the angles measure 60 degrees, which is less than 90 degrees. And in this case, this isosceles triangle is an acute triangle as well. Now, in this scalene triangle that I've drawn, it's a little bit close to see, but this angle could be greater than a 90-degree angle, which would make it obtuse. And knowing that the sum of the interior angles of a triangle are 180 degrees, I want you to consider this question of, can a triangle have two obtuse internal angles? So two angles that are greater than 90 degrees. And I hope you can right away tell that no, that's not possible, because as soon as one angle is greater than 90 degrees, even if it's by 1 degree, so let's say it's 91 degrees, then we know that the sum of the other two angles along with the 91 degrees had to add up to 180 degrees, which means that the other two angles will be 89 degrees and neither of them can be an obtuse angle. And finally, we have a right triangle, which is one we're going to use a lot in this lesson. And this is when you have a right angle. And I'm going to show you, oh, there we go, right here. With right angle triangles, it is that exactly one angle measures to 90 degrees, and it is shown with this little square there. And the side that is opposite to this 90-degree angle is going to be the longest side of that triangle, and it is called the hypotenuse. And the other two side lengths are just called the legs, and they can vary between vertical or horizontal depending on how you draw the shape. Also, when it comes to measuring or naming the side lengths, so I'll show you here before we move on. So if this is vertex A, then this is its corresponding angle A, and the side length that is opposite to it is a lowercase a. Same with this, we have vertex C, so this angle here and we don't know if those two are necessarily equal, which is why I'm doing two lines here. This will be angle C, and the side length opposite to it will be a lowercase c. And finally, this b here means that the hypotenuse is b. Now, with right triangles, because we have the Pythagorean theorem, we actually have a specific way of labeling the vertices so that we match it to the um, Pythagorean theorem. And I'll show you right below here. So the Pythagoras theorem or Pythagorean theorem is a rule in geometry that tells us in a right angle triangle, the square of each leg, when you sum it up, is equal to the square of the hypotenuse. So here we have one leg and another leg here, A and B. And a squared plus b squared is equal to c squared. Now, if you're curious why this is, I have included the proof of it. It has to do with the area of squares that can be formed based on these side lengths. And I have attached that for you on Google Classroom. So if you're curious, definitely check that out. But it is not a requirement for you to know the proof. So as long as you just know how to use this theorem when it comes to right angle triangles, that's enough for this course. So let's get some practice. Here we have a right angle triangle, and this is so actually, before I get started on that one, I am going to show you here. The reason I said we have a specific way of labeling these vertices, so because these legs always have to be A and B to match this equation, then this vertex opposite to the lowercase a will be an uppercase A. This vertex, which is opposite to the lowercase b, will be an uppercase B, and this vertex here will be an uppercase C. That's opposite to the hypotenuse. Now, this is a standard, but of course, you can always change the variables around as long as you know that the two sides that you're adding are the legs, and the one that is on its own is always the hypotenuse, which is the longest side in the right triangle. So now in this one, as you can see, it is not the ACB that we were seeing above, but we're still going to work with it and it's still going to produce an answer. So here we want to determine the value of A. So starting with my theorem, I know that A squared plus 12 squared, these are the two legs. This is the leg and this is the leg. So these two squared are going to be equal to 20 squared. So now I can evaluate each of those. So this is 144, and this one is going to be 400. And now if I rearrange, I will have a squared is equal to 400 minus 144, which is 256. And now you will take the square root of each of these. So don't forget your exponents here. And so taking the square root of the left-hand side, so this exponent and the square root will just produce a. And on the right-hand side, we get 16. So the measurement of the side length A is just 16. And in this case, because we aren't given units, we can just say, therefore, A is equal to 16 units. And as a good practice in math, it's always a good idea to square out your final answer, because as you can see right now with my solution, when I look at all the work, yes, I can see this work was done here. And right away, if I just want to check your final answer, I can see that this is your final answer because it's boxed out. And if this is correct and I can look at here and it's correct, then I know that you followed it right. But if I look at this right away and I see this is incorrect, then I can follow through your solution to see where you might have gone wrong. Now, in this next one, here we also have the one side length and the hypotenuse. So we're again solving for one of the side lengths, which is DE in this case. So you have one option here. You can either use DE, or because this is vertex F, I can label let DE or side length dE be equal to F. And I can also label this F here. Pretty much whenever you want to define a variable or use a variable, you have to define it. So you do have to put a let statement, or if you have a diagram, you have to label it on your diagram to show whoever's reading your solution what that variable is referring to. So now F squared plus 15 squared is equal to 17 squared. Again, remember, 17 is my hypotenuse, so it has to be on its own here. And now if I evaluate each of these, this is 225, the F squared stays, and then on the right-hand side, 17 squared is 289. So then F squared is equal to 64. And now you can see I'm skipping a few steps here. And so F will be equal to 8. I just recognize 64 as one of my perfect squares. So the side length F is equal to 8. So again, therefore, DE is equal to 8 units. And I will box this answer over here. Now, in this next example, we have side length Z already defined for us. And here, this is actually the hypotenuse here. So yes, I will point out that this is better if this was Y to correspond with this Y, but that's okay. We can still solve it. So here, 9 squared plus 12 squared. So these are my legs of this right angle triangle. These are going to be equal to Z squared. Now here we have 81 plus 144, and this is Z squared. So this will be 225 is equal to Z squared. And again, taking the square root of both sides, I will find that Z is equal to 15. And when I'm writing my final answer, therefore Z is equal to 15 units. And just as a check, whenever, especially when you are doing solving for the hypotenuse, I always recommend check, is 15 greater than both 9 and 12? And yes, it is. And that's what we would expect, right? Because the hypotenuse is the side with the greatest length, and that's exactly what we have right here. Now, for our next problem, we are told that a right triangle has side lengths such that one leg is 3 centimeters longer than the other leg. If the hypotenuse is 15 centimeters, determine the length of the two legs. So here's my let statement right here. So let x be the measure of the shorter leg, and because the longer leg is 3 centimeters longer, then we can write x plus 3 as the measure of the longer leg. Now, using Pythagorean theorem, and it is sometimes nice, especially when you get introduced to more and more theorems, to write which theorem you are using, even though it is, for the sake of this lesson, it is pretty self-explanatory because we're only working with Pythagorean theorem so far. But again, when you have theorems later on, so throughout this unit, you're going to see sine law, cosine law. So it is helpful to write which theorem you're using. So then x squared, and I'm putting brackets to show that x is the side length, and I'm squaring it, and then x plus 3 squared is equal to 15 centimeters squared. Now, I do have to simplify my left-hand side first, so this is just x squared, and maybe I need a bit more space there. And remember, this is, maybe I'll show you here. X plus 3 squared is really x plus 3 times x plus 3. And we use a distributive property here. So first multiply x by each of these terms. So x squared, and then x times 3 is plus 3x. And then now multiply the 3. So 3 times x is another 3x. And finally, the 3 and the 3 are 9. And if I simplify this, it's x squared plus 6x plus 9. And then I can just rewrite this back here. especially because I've already shown my work on that side. It's totally okay for me to write this here. And this is equal to 225. Now I will move this over and I will simplify on this side as well. Sorry, 2x squared plus 6x. And this is going to be, let me move it over. Just so I'm going to show you the extra step. It's plus 9 and then minus 225 is equal to 0. And if we find this, and right away, I do see that these are all multiples of 2, so I do have an option to factor out that 2 or divide all the terms by 2 so that I have x squared plus 3x and minus 108 is equal to 0. And now this is just a quadratic and it is equal to 0. So I'm going to give you a moment to pause and I want you to try and solve for what x would be equal to in this problem here. Factoring should have given you the following result, and now we can actually just solve for x. So in this bracket, x is going to be equal to negative 12, and here x is equal to 9. And remember, we are working with measurements, so we cannot have a negative measurement. So then we can say that this is inadmissible. And remember, that just means that that answer is not included in our domain, and so we cannot interpret it in the context of our problem. So then we do have x is equal to 9. So then the shorter side or the shorter leg, which was equal to x, is just 9 centimeters, and the longer leg was x plus 3, so it's going to be 12 centimeters. And now I can just try to visualize this. This would be 9 centimeters. This would be 12 centimeters, and my hypotenuse, which was 15 centimeters. And you can do a check for yourself. So I would box this as my final answer. And if we do a double check here, 9 squared plus 12 squared will give you precisely 15 squared. And so the Pythagorean theorem here holds, and that's our right angle triangle. So yeah, with problems like this, try to figure out the algebra first, and then you can always double check that it satisfies the requirements for a right angle triangle. Now we're going to be introduced to our primary or basic trigonometric ratios. These apply for right triangles, and they are also another way for us to be able to solve for different measurements of a right triangle, specifically for the angles and the side lengths. And it is also just, because it's a ratio, it is a comparison of the side lengths to the angles as well. So the primary trigonometric ratios are sine, cosine, and tangent. And in this right angle triangle here, we have to first define the angle that we are looking at. So this is the angle that's defined for us, and this is the symbol theta that is often used to label angles. And so the ratios are with respect to a specific angle. So if I choose this angle, my answers are going to be completely different. So I'm only looking at this angle right here. And there is a rule or a method to remember sine, cosine, and tangent, and it is SOHCAHTOA. So the OH tells us opposite over hypotenuse. So the sine of the angle theta here is going to be the ratio of the side length that's opposite to that angle over the hypotenuse. So in this case, this is the side length that's opposite to this angle theta, and the hypotenuse never changes. So that's the ratio we would have. The cosine, which is ka, is the adjacent side, so adjacent is next to, the adjacent side length over the hypotenuse. And finally, the tangent or TOA is going to be the opposite side length over the adjacent, so the hypotenuse is not being used here. And as you can see, each of these side lengths are being used twice in these ratios and they're accounted for there. And so we can see that from here, we can solve for each of these. Given an angle and a side length, we can solve for one of the other side lengths, or given the side lengths, we can solve for the angle as well. So we're going to see that in some of our examples today. And so again, don't forget, adjacent is the side length that's next to the angle, and opposite is the side length opposite. Now, if I choose this angle, and let's call this one beta. This is angle beta, or maybe I won't use beta. Okay, I'll actually use alpha. The reason I chose to not go with beta is because it looks a little too close to B. So we'll go with alpha there. So now, with respect to alpha, the side length that's opposite to it is going to be this side length. And this side length is the adjacent side length. So it does matter which angle. So you do have to know which angle you're given or make sure you are matching the side lengths correctly when you are evaluating these ratios. So let's look at our first example here. So here we're asked to determine the primary trigonometric ratios for angle alpha here and angle theta here. So let's start with angle, or I'm actually going to use the same colors there. So angle theta. So here we want the sine, the cosine, and the tangent. So first, just for myself, this is the opposite angle to theta, and this is the, or not the angle, sorry, the side length, and this is the adjacent side length. So remember, sine is so opposite over hypotenuse, so opposite over hypotenuse. So it's going to be 16 over 20. And this is a fraction. I can simplify this to 4 over 5. Now, cosine is going to be ka, so adjacent over hypotenuse. So adjacent over hypotenuse, and this is going to be 12 over 20. And now if I simplify this as well, we have 3 over 5. And finally, tangent TOA is opposite over adjacent, and it's going to be 16 over 12 or 4 over 3. Now, for alpha, and one thing also, you leave these as fractions. You don't need to evaluate them into decimal points. Fractions are okay. So now with alpha, this is the opposite side length, and 16 is the adjacent. And again, hypotenuse never changes. This is the hypotenuse for both of them. So now sine, let me just write out all of these first. Oh, whoops, not theta. There we go, alpha, alpha, and then tangent of alpha. So this is again, so opposite over hypotenuse. So it's going to be opposite 12 over hypotenuse 20. And this is 3 over 5. The cosine is going to be ka, adjacent over hypotenuse. So adjacent over hypotenuse. This is 16 over 20, which is 4 over 5. And finally, the tangent TOA is opposite over adjacent. And this is 12 over 16 or 3 over 4. And now take a moment and compare these. Do you notice any similarities, any differences? How can you compare the ratios? So as you can see, value here is the same as here. So the cosine of this angle is equal to the sine of this angle. And the sine of this angle is equal to the cosine of this angle. And the tangents are the reciprocal of one another. And of course, when we look at the triangle, that makes sense because the opposite and adjacent sides alternate depending on which angle we're looking at. And of course, the hypotenuse stays the same, which does result in this. And this is also a good way you can always check your answers that you should have these two ratios to be the same. And in fact, and we saw a few examples of this already and you didn't know it, but this is a special type of right angle triangle, and it's called the 3-4-5 triangle. So it starts with this triangle that it has a measurement of 3, 4, 5, any unit. It can be centimeters, kilometers, whatever. And as long as you multiply all the side lengths here by the same ratio, then you have these ratios hold for these triangles. So as you can see here, we have 12, 16, 20. This is the 3 times 4. This is the 4 times 4. And this is the hypotenuse 5 times 4. So that's why ultimately, when we calculate the ratios, we end up with that 3, 4, and 5 because it's really derived from this main type of right angle triangle. We also saw this in this example here. So if you remember, this was 15. So then this is the 3, 4, 5, and here we have a multiple of 3. So this is also that 3, 4, 5 triangle. And if you calculate the ratio of these two angles, you will get the same as the ones we just got in the alpha and theta example. And also here as well, this is that 12, 16, 20, which is the times 4 of the 3, 4, 5 right triangle. So you can always sometimes you'll be given problems of, is this a right triangle? And if you can see this ratio there and have that right angle there, then you can conclude that this comes from this basic right angle triangle. Now, in this next one, we again want to determine the primary trigonometric ratios for alpha and theta. So I'm just going to do it a little bit faster, so I won't write everything here. So starting with, maybe let me do, this one can be blue. And let's make this one red. So here, sine of theta is going to be the opposite over hypotenuse, 12 over 13. The cosine is going to be the adjacent over the hypotenuse, 5 over 13. And the tangent, TOA, is going to be opposite over adjacent, so 12 over 5. Now, for alpha, the sine of alpha is opposite over hypotenuse. And I can already see this is equal to this sign here, which is what I want. The cosine, this should also be equal to this sign here. So the cosine is adjacent over hypotenuse. That's exactly what we see. And finally, the tangent, TOA, opposite over adjacent. So opposite over adjacent will be 5 over 12, and that's exactly the reciprocal over here. And one thing I'm going to note as well, trigonometric ratios don't actually have a unit. They're a ratio because consider this to be centimeter. So if you have 12 centimeter divided by 13 centimeter, the centimeters are going to be simplified or cancel each other out. So then you're only left with the ratio of 12 over 13. So then we don't actually have units for these. And this is also a special type of right angle triangle, and this has ratios 5, 12, 13. So you might see, for example, 10, 24, 26. So that will be the double of these ratios. So it comes from this basic right triangle. Now, in this next one, we are told the angle here is 28, and we want to use trigonometric ratios to solve for the unknown side length. So I will show you maybe two different ways. So First, I can see that with respect to this angle, and this is 28 degrees, and side length x is opposite. So I either want to use sine, which has opposite over hypotenuse, or I want to use tangent, which is opposite over adjacent. And because in this case I am given both the hypotenuse and the adjacent side length, I can do either or. So here's now where you're going to use your calculator, and we have to evaluate sine of 28. But I will simplify a little bit more because I want to solve for the opposite side here. I know that sine of theta is times the hypotenuse. So then I will say that x is equal to sine of 28 degrees times the hypotenuse, which is 17. And the reason I do this is because sine of 28 degrees is going to give you a decimal. So then when you have one expression and you just input that into your calculator, you get the most exact answer. And in this case, we get x is equal to 7.98. And yeah, we don't have any units here, so I would just write units. Now I'll show you that you should get the same answer if you are using tangent. So tangent here to solve for the opposite side. So opposite here will be tangent of theta times the adjacent side. So in this case, I have x is equal to tangent of 28 degrees times the adjacent side here, which is 8. So times 8. And now if you input this into your calculator, and I will just do it to double check. So actually a minor correction here. This is incorrect. This one should be 15 for this to work because the ratios have to hold based on this angle. And if I have this angle 28, 8 over 17 would not be the cosine. So this has to be 15 because as I was solving, it wasn't working out. There we go. So if this is now 15, and then we solve for tangent of 28 times 15, this will also produce x is equal to 7.98 or approximately 8 units. And so we can see that through either of these solutions, I was able to receive that same side length or measure of the side length. And now let's look at our next example. Here we are told that alpha here is equal to 37 degrees. And so we want to solve for the unknown side length here, which is y. So with respect to alpha, y is the adjacent side. So again, we can use either cosine of alpha here, which will give us adjacent over hypotenuse, or we can use the tangent, which will be opposite over adjacent. So starting with the cosine, cosine of 37 degrees is going to be equal to y over 20. So then y is going to be equal to cosine of 37 degrees times 20. And if I just use my calculator here for this, we get that y is equal to approximately 15.97. And I should get the same result using the tangent, but in this case, because I'm solving for adjacent, so just to do a little bit of rearranging, this is going to be equal to opposite divided by tangent. So then y is equal to 12 and then divided by tangent of 37 degrees. And let's check this now. And that's precisely what I get. It is a little bit off by for the decimal, so perhaps maybe we just round it to, this will give you 15.9. So we can say y is approximately 15.9 units. And then again, I'm just going to box my answer there. Now, in this final example, again, we're solving for one of our unknown side lengths. So here you can choose which method to use. I'll maybe only show you one for this so you can double check with the other method. And so here, side length Z is opposite to theta. So I will use sine of theta is equal to opposite over hypotenuse. And in this case, it'll be sine of 53 degrees is equal to Z over 15. And so Z is equal to sine of 53 degrees times 15. And we get, in this case, Z is approximately 12, just 12 units. And that's precisely R345 or almost R345 triangle with a ratio, or it's multiplied by a scale factor of 3 in this case, and it is approximately the angles that we would expect here. So double check using another ratio that you also get 12 units here. And just one last question I'm going to leave you off now, as you saw some of these examples, is whether I needed to give you both of these side lengths for you to determine theta, or was it enough for me to just give you one of them? Consider, for example, if in this case, I didn't give you this 9 here. So this was, I can even white it out there. And as you can see, even without that 9, I'm still able to follow through with this solution here because I only really needed the 15 and the angle. Now, I can challenge you also to think, if you were only given one of the side lengths, how can you determine both of these two side lengths? And of course, we are still using, we have two options here. You can definitely use trigonometric ratios. So I can use sine to find z, and then I can use cosine, and I can solve for this side length here, and you should get 9 with respect to 15. Another way is also, once you have 12, you have a right angle triangle with two side lengths. Then you could have also done Pythagorean theorem to do 15 squared minus 12 squared, and you would have got 9 squared, which would give you the side length of 9 here. So, lots of connections between Pythagorean theorem and trigonometric ratios. And for this lesson, you do have a practice set where you can input all your answers, and it does actually give you the correct answer right then and there, so you can double check. Just make sure you're following the guidelines. And again, check Google Classroom for any additional tasks or extra readings that can support your learning. And don't hesitate to reach out if you have any questions, and I'll see you all in our next class.